What specific problem does your proposed counterfactual token generation method aim to solve that existing large language models cannot address?
The proposed counterfactual token generation method aims to solve the problem of enabling large language models, LLMs, to conduct counterfactual reasoning about their outputs, which current LLMs cannot do due to their stateless design. Specifically, existing LLMs generate outputs through an autoregressive process that lacks the ability to maintain internal memory or state, making it impossible to determine how the model would have responded if a previous token had been different. Our method augments this autoregressive process using a Gumbel Max Structural Causal Model, SCM, which allows for the specification of how the sampler would behave under interventions on the token distribution. This enables the generation of counterfactual outputs that are consistent with the underlying model of the world constructed by the LLM, addressing the limitations of existing methods that do not account for the stochastic nature of token selection. Ultimately, this approach facilitates more accurate counterfactual reasoning and analysis, including applications in bias detection.
How does the proposed method work? Please illustrate the step-by-step process, including how the Gumbel Max Structural Causal Model is integrated into the token generation process.
The proposed method integrates the Gumbel Max Structural Causal Model, SCM, into the token generation process to enable counterfactual reasoning in large language models, LLMs. First, the autoregressive token generation process is augmented by defining a causal mechanism that takes as input the distribution of the next token and a set of Gumbel noise values. Specifically, the function for sampling the next token is expressed as f_t_p_i u_i equals text argmax versus in v log p_i t_i equals v plus u_iv, where u_iv are independently distributed Gumbel variables. During counterfactual generation, the same noise values used in the factual generation are reused, ensuring that the output sequence remains similar to the original, thus satisfying the property of counterfactual stability. The process involves first modifying the input sequence, e.g., changing a token, and then regenerating the output using the augmented autoregressive process, which allows for the deterministic generation of counterfactual outputs based on the original stochastic behavior of the model. This method not only facilitates counterfactual reasoning, but also allows for efficient sampling with minimal additional memory requirements.
Could you provide a simple illustrative example that walks through the main steps of your proposed algorithm and illustrates how it generates counterfactual outputs?
To illustrate the main steps of our proposed algorithm for generating counterfactual outputs, consider the example of a story about a captain named Lyra. Initially, the LLM generates a story based on the prompt, resulting in a factual output. If we want to change the captain's name from Lyra to Maeve, we first modify the input sequence by replacing Lyra with Maeve. The key step in our algorithm is to reuse the same noise values, u_j, that were used during the original generation, ensuring that the stochastic state of the sampler remains consistent. This is achieved through the Gumbel Max Structural Causal Model, SCM, which allows the model to generate the counterfactual output while maintaining the same initial tokens. As a result, the counterfactual story begins identically to the factual one, demonstrating the property of counterfactual stability, although it may diverge later due to the sensitivity of the LLM's token distributions to minor changes.
What are the theoretical or practical advantages of using your counterfactual token generation method over traditional autoregressive token generation methods?
The counterfactual token generation method, as proposed in this work, offers significant theoretical and practical advantages over traditional autoregressive token generation methods. Firstly, it incorporates a Gumbel Max Structural Causal Model, SCM, which allows for counterfactual reasoning by maintaining the same stochastic state of the sampler during token generation, thus ensuring counterfactual stability. This stability means that the counterfactual outputs are more likely to resemble the factual outputs, as demonstrated by lower edit distances in similarity analyses. Practically, the method enables efficient counterfactual token generation with minimal additional memory requirements compared to vanilla token generation, as it only needs to store the state of the random number generator rather than all noise values. Additionally, this approach can be utilized for bias detection, revealing inconsistencies in the model's perceived relationships between sensitive attributes and outcomes, which traditional methods may overlook.
How did you validate or test the effectiveness of your proposed method? What datasets and metrics did you use to demonstrate its performance?
To validate the effectiveness of our proposed counterfactual token generation method, we implemented it on the Llama 3.8b instruct model and conducted a series of experiments. We sourced 2,000 question prompts from the LMSYS Chat1M dataset to generate factual outputs, followed by 2 types of interventions where we replaced a randomly selected token in the output. We then measured the similarity between the regenerated second part of the output and its factual counterpart, using the normalized Levenshtein edit distance as our metric. The results indicated that the output sequences generated through counterfactual token generation exhibited lower edit distances compared to those generated via interventional token generation, demonstrating that our method effectively prioritizes the selection of tokens consistent with the factual generation. Additionally, we applied our methodology to a census data generation task to investigate potential biases, further showcasing its practical utility in analyzing model behavior.
What specific results and findings did you achieve through your experiments, particularly regarding the similarity of counterfactual outputs compared to factual outputs?
Through our experiments, we quantitatively analyzed the similarity between counterfactual outputs generated using our Gumbel Max SCM approach and the original factual outputs. We measured this similarity using the normalized Levenshtein edit distance, which indicated that counterfactual outputs were more similar to their factual counterparts than outputs generated through interventional token generation. Specifically, the results showed that the edit distance was lower for counterfactual token generation, suggesting that this method effectively prioritized selecting the same tokens as in the factual generation. Additionally, we observed that even when employing top P and top K Gumbel Max SCMs, which are not guaranteed to maintain counterfactual stability, the counterfactual outputs still exhibited a tendency to align closely with the factual outputs. This reinforces the effectiveness of our approach in generating counterfactual text that retains significant similarity to the original factual text.